In this lecture today, now we'll be looking at some more examples on linearization. Let's take the case of simple pendulum that we have discussed. For a simple pendulum, the state space model is x1 dot equal to x2 and x2 dot is equal to minus g by L sine of x1 plus tau by ml square. We are taking an unforced simple pendulum and we'll try to see whether this system, how we can linearize this system model and how we can then find out whether the system is controllable, if it is observable, and if it's stable or not. Now, first of all, equating x1 dot equating x dot equal to 0. That means x1 dot is equal to 0, which implies x2 is equal to 0, and x2 dot equal to 0 means minus g by L sine of x1 is equal to 0, which implies x1 can be 0, it can be pi, it can be 3 pi, but since all those other values are repeat, they are just 3 pi is actually equivalent to 0, 4 pi, 5 pi will be again equivalent to pi only. So we can say there are x1 and equal to 0 and pi represent all the angles covered in that 4 quadrant and therefore what we have is the equilibrium points. We have 0 0 and pi 0. So we have two equilibrium points in this case. Secondly, now we need to find out A matrix, which is given by delta f1 by delta x1, delta f1 by delta x2, del f2 by del x1, del f2 by del x2. Our first function in this case is x1 dot equal to x2. This is f1. x2 dot equal to minus g by L sine of x1. This is our function number 2, f2. Fine. So this is actually f1 of x comma u. Since there is no u involved here, we have assumed that input we have an unforced simple pendulum. We are not actually having a constant input being applied to the system. We try to see the motion, the behavior of the simple pendulum, whether it is stable or not, whether it's controllable or not. So del f1 by del x1, that means actually differentiation of x2 with respect to x1. Differentiation of x2, f1 is x2, x1 dot equal to x2, and f2 is x2 dot equal to minus g by L sine of x1. So what we are getting here is if we differentiate the first function with respect to x1, it is 0. First function with respect to x2, it is 1. Second function with respect to x1, it gives us minus g by L. Sine of x1 is cos, and df2 by dx2, that will be 0. And this is at your initial operating point, your equilibrium point x0. We have already derived the equilibrium point in this case. We have two equilibrium points in this case. For x0 equal to 0 comma 0, A matrix will be equal to 0 1 minus g by L cos of 0. Cos of 0 is 1, so it's minus g by L 0. And for x naught equal to pi 0, A matrix will come out to be 0 1 minus g by L cos of pi. Cos of pi is minus 1, so this becomes plus g by L 0. Fine. So this is our A matrices, and therefore our linear model now comes out to be, it can be represented by x dot equal to ax plus bu. In this case u is 0, so which implies x dot equal to 0 1 minus g by L 0 x, or x dot equal to 0 1 plus g by L 0 x. So what you are getting, now you have a linear model, you have obtained linear model, but because of multiple equilibrium points for this non-linear system, you are getting multiple linear models as well. So it's not going to be straightforward case where we will be saying that we'll be actually getting from both these two models different sets of eigenvalues, and one set of eigenvalue may say this system is stable, another set of eigenvalue may say this table is unstable. It can do that. So this actually represents the behavior of the actual nonlinear system. As I said to you, when we talk about stability of nonlinear systems, we do not talk about stability of the system as a whole. We talk about the stability of an equilibrium point. So a system will be stable around one equilibrium point, while as it can be unstable around another equilibrium point. So first case where our origin was the equilibrium point or the operating point, the eigenvalues of the system, if you see, this is a lambda square plus g by L. That means lambda will be equal to plus minus under root of g by L iota. For this case where our equilibrium point was pi 0, yes, our eigenvalues for this system, lambda I minus a, determinant of lambda I minus a equating that to 0, you can find out the values of lambda 1 and lambda 2. Fine. So lambda I minus a, equate this equal to 0, you can get the values of lambda 1 and lambda 2. So once you do that, this becomes lambda square minus g by L, that is lambda square is equal to g by L. So that means lambda is equal to plus minus under root of g by L. So in one case, lambda 1, lambda 2 is coming out to be plus minus under root of g by L iota. And in another case, lambda 1, lambda 2 is coming out to be plus minus under root of g by L. So if we plot this in the S-plane, so for the equilibrium point 0 0, lambda 1 is under root of g by L I and minus under root of g by L I. For the equilibrium point pi 0 means that will be somewhere here. Our equilibrium point is plus minus under root of g by L. That means one of our eigenvalues is here, another eigenvalues can be it is actually a mirror image of this. So let us say it is here. So this is under root of g by L minus, and this is under root of g by L plus, and this dot here is actually your equilibrium point, that is pi 0. So I'm trying to actually show with respect having both x1 and x2 as well as the S-plane in mind. So with respect to this equilibrium point, the system is marginally stable. So this is the sort of behavior actually what we may see in case of a simple pendulum. For a marginally stable system, for these two rods on the imaginary axis, the output response is undamped. That means oscillatory behavior is exhibited, and this is a case that we see in case of simple pendulum. Fine. An oscillatory behavior, that is sustained oscillations. And in another case, what we are seeing is 2 points which are located at they are actually, one is located, they are two equal but opposite signs real roots that actually will be defining these points as well, and this actually corresponds to saddle points. So this is an unstable system. So what we will be seeing, there may be a case where, depending upon the initial condition of the pendulum, your system may not stop and swing back. It will rotate in the same direction, and it will fall out of synchronization. Fine. If you have a simple pendulum, because of the position where it was held, and because of the rotation of motion, your simple pendulum will not show an oscillatory behavior. It will exhibit a complete circle. Fine. So for example, like this, I put a pendulum here and I am releasing it. Because of the inertia that it will gain, it can have a whole rotation that may lead to this that may lead to this unstable behavior, and it will then come again to stop. But because of this rotation, because of the complete cycle, the system was out of synchronization, and we'll say this system has exhibited an unstable behavior. So this might be a case. It's not actually going to happen always. So with respect to nonlinear systems, that's what the case is. Our system is not going to be simply stable. Our equilibrium points are going to be stable. So you have one equilibrium point for this particular case, that is 0 0, that is marginally stable, and you have another equilibrium point, that is pi 0, that is unstable. It has an eigenvalue that's in the right half of the S-plane, and therefore this system represents an unstable system. Right? Now let us look at the controllability, whether this system will be controllable or not. Since we do not have the B matrices, so it's not going to be possible for us to check the controllability matrix. For that, we would have taken a case where we would have forced the system and said that this system is controllable or not. So we'll do that. We'll also do that in a while. Let's take another example, and using that example also try to see whether for multiple equilibrium points how we can check this case of stability. You have a system whose state space model is given by x1 dot equal to So let us see first of all whether this has multiple equilibrium points or not. So let us not take this example. I'm not sure about the number of equilibrium points. Let us have this example. So you have x1 dot equal to x1 minus x2 square and x2 dot equal to x1 plus x2. X1 minus x1 square. Fine. So we have this system. Let's first of all check the equilibrium points for the system or the operating points. Again, this is an unforced system. X1 dot equal to 0. Implies x1 minus x1 square is equal to 0, which implies x1 1 minus x1 is equal to 0, which implies x1 is equal to 0 comma 1, and x2 dot equal to 0 implies x1 plus x2 equal to 0, which implies x2 is equal to minus x1, which implies x2 is equal to 0 comma minus 1. So corresponding to x1 equal to 0, x2 will be 0. Corresponding to x1 equal to 1, x2 will be minus 1. So we have therefore the equilibrium points 0 comma 0 and 1 comma minus 1. So these are our equilibrium points. Now with these equilibrium points, we need to linearize the system. We need to find out the A matrix df1 by dx1, df1 by dx2, df2 by dx1, df2 by dx2. So df1, f1 is x1 minus x1 square, f2 is x1 plus x2. So differentiating f1 with respect to x1, it comes out to be 1 minus 2x1. With respect to x2, it is 0. With respect to x1, it is 1. With respect to x2, it is 1. So this is our A matrix for 0 0 for the equilibrium, for the first equilibrium point. A matrix when we substitute x1 equal to 0 here, x2 equal to 0 here, what we'll be getting is 1 minus 0, so that is 1 0 1 1. Fine. And for one minus 1, when we substitute 1 here, this 1 minus 2 that becomes minus 1 0 1 1. So these are two A matrices. So we can have the linearized model of the system is therefore 1 0 1 1 x, or x dot equal to minus 1 0 1 1 x. Fine. And eigenvalues, substituting lambda I minus a equal to 0, we'll get the eigenvalues 1 comma 1, and we'll get the eigenvalues lambda plus 1, lambda minus 1, so we have plus minus 1. So in either of the two cases, the system is unstable. You have both roots on the right of the S-plane, you have one root on the right of the S-plane. So this system is basically on both corresponding to both equilibrium points. The system is exhibiting unstable behavior. So far we haven't seen a stable system in all of the examples that we have taken. Let's have one more example. x1 dot equal to minus x1 plus 2 x1 square x2 and x2 dot equal to minus x2. So the first thing is substitute x1 dot equal to 0. Once you substitute x1 dot equal to 0, equate this equation to 0. And x2 dot equal to 0, which implies minus x2 equal to 0, or you can say x2 equal to 0. Substitute the value of x2 dot equal to 0 here, so this comes out to be minus x1 equal to 0, which implies x1 equal to 0. So in this case we have actually only one equilibrium point, and that is 0, 0. Linearizing this by finding out the A matrix, delta f1 by delta x1, delta f1 by delta x2, delta f2 by delta x1, delta f2 divided by delta x2. Our f1 is minus x1 plus 2 x1 square x2. Our f2 is minus x2. So when we differentiate the first equation f1 with respect to x1, so this comes out to be minus 1 plus 4 x1 x2, fine, and differentiating it with respect to x2, we get minus x1 plus 4 plus 2 x1 square. Differentiating f2 with respect to x1, it is 0. Differentiating it with respect to x2, it is minus 1. So substituting x1 x2 equal to 0, 0. The A matrix that we'll be getting is minus 1, 0, 0, minus 1. So the linearized model that we have, x dot equal to ax, for this particular case it is x dot equal to minus 1, 0, 0, minus 1 times x. So, and lambda 1, lambda 2 for this case, this is lambda plus 1 into lambda 1 plus square, so that's actually minus 1, minus 1. So you have a system which is having a stable equilibrium point. This is not a marginally stable, this is not unstable, this is a stable equilibrium point. So we have a nonlinear system, dynamic model of a nonlinear system whose equilibrium point is stable in nature. Let's now take an example of a forced system. x1 square equal to x1 plus x1 square x1 minus x1 square plus u x2 dot equal to minus x2. Say for example we have a system like this, we want to see the behavior of the system. Now for finding out the equilibrium points of such systems, you have to equate u equal to 0, fine. You have to equate x1 dot equal to 0, x1 dot equal to 0, and you have to equate x2 dot equal to 0. x2 dot equal to 0 gives us minus x2 equal to 0, that means x2 equal to 0. x1 dot equal to 0 gives us x1, 1 minus x1 is equal to 0, which implies x1 is equal to 0 comma 1. Fine. So we have x1 x2 0 comma 0 and 0 1 comma 0. These are our equilibrium points with u equal to 0. A matrix delta f1 by delta x1, delta f1 by delta x2, delta f2 by delta x1, delta f2 by delta x2, where our f1 and f2, f1 is x1 minus x1 square plus u, and x2 is f2 is minus x2. So differentiating the first equation, the first function with respect to x1, we get 1 minus 2x1. Differentiation of u with respect to x1 will be 0. Differentiation of this with respect to x2 will be 0. Differentiation of this with respect to x1 will be 0. It will be minus 1. Fine. This is our A matrix, but we have to find it where? At x1, x2 equal to 0. And x1, x2 equal to 1, 0. So at this point, A matrix will be equal to 1, 0, 0, minus 1. At this point, it will be equal to, this is actually the previous example, only I am including the U matrix also here. Now we have to find out B matrix also for this case. So it will be delta f1 by delta u, delta f2 by delta u. So f1 had, if we look at f1 and differentiate this with respect to u, it will come out to be 1. The f2 has no dependency on u, so it will come out to be 0. Once we equilibrium points we substitute here, they are actually 0, 0 only. So x dot equal to ax plus bu will represent the complete model in this case. So 1 will be having 1, 0, 0, minus 1 times x plus 1, 0 times u, and we'll be having minus 1, 0, 0, minus 1 times x plus 1, 0 times u. So this is how we can obtain the linear model, the linearized model of nonlinear systems governed by nonlinear differential equations, and whether they are forced systems or unforced systems. We can actually try to find out lambdas, eigenvalues of the system. Besides that, we can find out now the controllability matrix for the system, and we can actually see whether this system is controllable or not. We are not actually going to be dealing with the C matrix, so we are not going to be touching observability here. So for controllability matrix, we have to find out the rank of controllability matrix B, AB. So in this case, B is 1, 0. And you can, if you find out 1, 0, it will be actually 1, 0 again. This is for this case, and for this case it will be minus 1, 0, 0. 1, 0, 1, 0, yes, fine. So we can actually so this particular example, you can see what is the controllability matrix. It does not have a rank equal to 1, so this is not a controllable system as well. But you can look for other systems. You can find out systems where the nonlinear model, once you have the linearized version, whether it is a controllable matrix or not, you can try to find that. So with these examples, I'll actually be forwarding you an assignment with regards to this linearization. You will cover that, you will forward that. In the next session, we actually have to study 3 methods: phase portrait, describing function, and the Liapra method. We'll be starting with the phase portrait method, because the phase portrait method involves the use of state space models, and we will it's a graphical analysis tool, so that will be taken up in the next session.